Course 3, Lesson 73, we are looking at formulas for sequences, and we are going to be using subscript notation in order to write formulas for these and find different terms in the sequences. So, let's look at, first of all, remember that a sequence is just a list of numbers that follows a certain rule. And we have different types of sequences. Our most common are things like arithmetic and geometric. We also have a way to talk about each of these different terms. And kind of like if you were thinking about x and y for a function, we talk about the number of the term, so what position it's in. Is it in the first, second, third, fourth, fifth position? And what is the value of the term? So in this sequence that we have on the bottom of the page, the second term has a value of 6, and the fourth term has a value of 12. Now we can have formulas for these sequences, like this one is a sub n is equal to 3n. What that means is if I change that n, which represents the position of a certain part of this sequence, if I replace that with an actual number, so let's say I want to know and check my formula for a sub 3, so the third term, I'm looking at this one. Well then, if I replace my a sub n with a sub 3, I'm also going to replace, well, my other n with 3. So I have 3 times 3 is 9, so that worked. How about a sub 5? Well, that would mean I'm doing 3 times 5, which is 15, which is exactly what my sequence said. So if I want to find the 8th term and the 11th term, that just means I need to replace a sub n with a sub 8, and we have 3 times 8, which is 24. And a sub 11 is 3 times 11, or 33. So I can replace my n, my position, with any number that I want in order to find the value of that position. Now sometimes these rules can be pretty difficult to write, so sometimes we just want to continue the sequence without a rule. So for example, maybe for this first one, we say, okay, 2, 4, 8, 16, 32. For this, it doesn't look like we're going up by a certain amount. We're not adding a certain amount every single time, but we are multiplying by a certain amount. We're multiplying by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. So we can continue by just finding the pattern and continuing it. So with this one, 1, 1, 2, 3, 5, 8, this one is actually a very special pattern. It's called the Fibonacci sequence. What it does is it takes the previous 2 terms, adds them up to get the next one. So for example, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, 5 plus 8 is 13, and 8 plus 13 is 21. So we need to find that pattern. And our next and last one, 1, negative 2, 2, negative 1, 3, 0, 4. Well, it looks like we're kind of going back and forth into positives and negatives. So let's see if there's maybe a consistent pattern as far as adding or subtracting. Let's see, so 1 to negative 2, we subtracted 3. And then negative 2 to 2, we added 4. 2 to negative 1, we subtracted 3. Negative 1 to 3, we added 4. Subtracted 3, added 4. Subtracted 3, so we get to 1. Added 4, we get to 5. So my next terms would be 1 and 5. Now, let's try and write a rule for this sequence that we saw just a minute ago. 2, 4, 8, 16, 32. Now, if you remember, between our 2 types of sequences, arithmetic or geometric, this has a constant ratio. We are multiplying by a certain amount each time, so this is geometric. Okay, so let's see. Our geometric sequences start with a sub n is equal to our first term, a sub 1, times our common ratio, in this case 2, to the n minus 1 power. That's what we learned in a previous lesson about these sequences. So we can say, in this case, a sub n is equal to, well, our first term is 2, and we're multiplying by a ratio of 2 to the n minus 1. Now we can actually simplify this one. Some of these we cannot. This one we can because we can think of this first 2 as 2 to the first power. So when we're multiplying things with the same base, we add the exponents. So we're actually adding n minus 1 plus 1. So we just get 2 to the n power. Meaning if we're thinking about these in positions, this would be 1, 2, 3, 4, and 5, we could say a sub 2 should be 2 squared, which is 4. That worked. And maybe a sub 4 is 2 to the 4th power. Well, we get 16, which is correct. Now we want the 10th term, a sub 10, which is just 2 to the 10th power. That's a really big number. You can multiply it out, but we will get the 10th number with that geometric sequence. All right, let's find some of these sequences with this given formula. So I want to know the first 3 terms, so I'm going to be doing a sub 1, which means I have 1 plus 2 times 1. Well, 1 plus 2 is 3. And then a sub 2, meaning I'm going to be doing 1 plus 2 times 2, which is 4 plus 1, so 5. A sub 3 is 1 plus 2 times 3. Remember, I'm just replacing n with which position I want, so I have 7. So my first 3 terms are 3, 5, and 7. Okay, now what if I know that one of the terms in the sequence is 37? How do you find which position it's in? Well, my a sub n gives me the value of a certain position. So I could say, actually, I'm going to take this 37 and plug it in right here so that I have 37 is equal to 1 plus 2 times a certain position. So I can work backwards, subtracting 1 and get 36 is equal to 2n. So n must be equal to 18. This must be in the 18th position. Now we have another special sequence. These are triangular numbers because literally they can be formed, all of these numbers, 1, 3, 6, 10, 15, can be transformed into triangles with a certain amount of dots. Now there's another reason that we call these triangular numbers. It's because another way that you could draw these is, let's say I'm drawing number 3. So we have 1, 2, and 3. Now if I were to have another triangle to make this a rectangle, I would have 1, 2, and 3. We would have this, the second triangle, and we have a rectangle. Now, when we look at this sequence, we have the first, second, third, fourth, and fifth. So we're saying, if we're looking at this rectangle that I just drew with this triangular number, we can say this side length of 2, well, that actually refers to this position of 2 right here. And this side length on the top would be 2 plus 1, so n plus 1. Well, to get the area of a triangle, typically I take base times height and divide it by 2. And that's exactly what happens with these triangular numbers. We have a sequence here that is shown by this formula of n times n plus 1 divided by 2. This works with any of our triangular numbers. For 6 it works. Let me show that. 1, 2, 3, 4, 5, 6. So we have our first triangle with side length of n. And then we have our next triangle, 1, 2, 3, 4, 5, 6. So we have our second triangle here. And we have a side length of n plus 1. So our triangle, our original triangle 6, is n times n plus 1 divided by 2. So when we find the 10th triangular number, all I'm going to want to do is do a sub 10 is equal to 10 times 10 plus 1 divided by 2. So we get 10 times 11 divided by 2, which means we have 55. Okay? All right. Just a couple more examples here. Find the 7th term in this sequence. Well, it looks like we're looking at square numbers. So if the first one in a position of 1 is just 1 squared, this one's 2 squared, 3 squared, 4 squared, meaning the 7th term would have to be 49. All right, the following sequence is generated with the formula a sub n equals 5n minus 2. Find the 10th term. Well, that's all we're going to do is just say a sub 10 is equal to 5 times 10 minus 2. So 50 minus 2 is 48. My 10th term in the sequence is 48. And which formula works for the sequence 0, 3, 8, 15? Well, let's see. Let's take each of these formulas and figure out what is maybe, let's say this fourth one. Let's say the fourth one. So if I do a sub 4 for each of these, a sub 4 for this one is 4 minus 1 or 3. That one's not going to work. A sub n, so we do a sub 4. So we have 2 times 4 minus 1, so 8 minus 1 is 7. That's also not going to work because we're looking for that 15. And last one, a sub 4, so we have 4 squared minus 1, or 16 minus 1, so we get 15. That one works. We can try it for all of the other ones, but it does work because each one of those is actually one less than its square. All right, and we'll just do a couple more, 2 more examples here, and then we'll finish. So a sub n, what are the first 4 terms of this sequence? Well, we'll do a sub 1 is equal to 1 squared plus 2 times 1 plus 1. So we have 1 plus 2 plus 1 is 4. And a sub 2, so we have 2 squared plus 2 times 2 plus 1. We have 4 plus 4 plus 1, so we get 9. A sub 3, 3 squared plus 2 times 3 plus 1, so we have 9 plus 6 plus 1 is 16. Interesting pattern so far. A sub 4, we have 4 squared plus 2 times 4 plus 1. So we have 16 plus 8 plus 1, and you probably have guessed it, this one is 25. Interestingly enough, soon we'll be factoring these type of quadratics. We would say this is actually n plus 1 squared. So whenever we do this, when we have a position, if we have the first position, we're doing 1 plus 1, so 2 squared is 4. Or let's say the fifth position, 5 plus 1 squared, our fifth one would be 36. Okay? And then lastly, what is the 20th triangular number? We're going to do a sub 20 is equal to 20 times 20 plus 1 divided by 2, which means I'm actually going to simplify this. So we have 10 times 21, which means my 20th triangular number is 210. Well, I hope this is helpful for your homework and for studying.